Okay, so let's revise this. So using binary search, we start with the invention of binary tree. Okay, so what this is it will be implemented very much like a doubly linked list, because it will just be a struct which has a val and a left pointer and a right pointer, but the overall connections will be completely different. Okay, instead of one dimensional, this will be a two-dimensional object, so it will look like that. This graph, so you have a pointer to the root, and then if you follow the other two pointers, you will go in either the left or the right subtrees, respectively. So we will use these terms. So say unique root, multiple edges, multiple internal nodes, leaves. Every node has incoming edges maximum 1 and outgoing edges maximum 2. So this is why it's called a binary tree. Then we had these functions define parent, child, left child, right child, which you can think of in the C implementation. It will be basically a struct where u dot left child or u dot left will give you the left child, and u dot right will give you the right child. And subtree of v, that also is a function. Height. So the parameters of a tree are height of a tree or a node and depth of a node. So some corrections here. So this I have added now this part plus 1. So for all nodes V, the height of V is height of its subtree the subtree at V was defined where? Yeah, so okay, no, so this should not be plus 1 then. That's fine. So height of V is the same as height of the subtree. Okay, so this is all done. Then we had an example of skew binary tree, because this is just as the height is not much as the number of nodes. So that's very skewed. So in applications actually we will need balance on both the left and the right side at every node. Okay, so we want to formally define what is a balanced binary tree. So this is defined by the two height differences. So difference of height should be at most 1. Equivalently, we can consider so this I have written, last time it was not there. We can consider distances to the leaves. Okay, so the farthest leaf on the left and farthest leaf on the right. We can also look at that. So that example is here. Numbers are now changed. So at the root we have 3, 2, because we are actually looking at the distance of the farthest leaf on the left side of the root. So that is that comes down to this. Okay, so that's 3, and on the right side you can consider this. So that is distance 2. So 3, 2, so which is fine. And you can see that everything was fine in the orange tree, but when you add so orange tree is balanced, but when you add this green node, then it creates a problem. Okay, so this green shaded node will immediately make the distance from that orange node, it will be 2, and as you move above, the problem will cascade. So there you will get 1, 3, and at the root you will get 4, 2. So at every level you have a problem. Okay, so this is an unbalanced tree. Is that clear? Any questions? So, why did I define this notion of balance, right? What will be the use in programming or in applications, in practical applications? So, this has actually huge utility, as you will very soon see. So, we want to understand the height of a balanced binary tree. So in terms of number of nodes, so if the number of nodes is n, what do you think is the height when the tree is balanced? You already know log n. Why is that? What is the proof of that? So you only know the answers, you don't know the proof. But this is not, the height is not equal, height can be different. So in this tree, the doubling that you are talking about, it's not actually happening. Look at the green bubble, and so that's the only child of its parent. So doubling, you don't even have the base case, right? So basically, when you look at the green bubble, it is only 1, and it's including the parent, you have 2, including the grandparent, it is 3. So 1 to 2 to 3. So if you see, it's not actually 2:1. Doubling is not happening at any stage. No. Even with orange, you start with the orange, then orange is 1, then parent is 2, and if doubling was happening, then you would have for height 3, 8, right? Do you have 8? You have 8. Yeah, but that's, so I can remove one. I can remove this one. This is not balanced. Why not? Where is the problem? What I have changed is just this number to 0. Everything is balanced. So it is balanced, but there is some leeway in the heights of the two children or two subtrees. So doubling is not so precise. Everything here is approximate. Okay, so you have to give a formal proof that for n nodes, what can be the maximum height? It may be more than log n. And in the worst case, it can be n. So this has to be, actually, you have to calculate this, and the calculation will go to the very first week of this class, of this course. It's not trivial. Yes? No. We have seen this. Array is a tree. Array is a binary tree. But a binary tree is not an array. So the formal proof goes like this. So we are interested in this function, minimum number of nodes for height h. So nh is defined as minimum number of nodes in a balanced binary tree of height h. So, well, height h, or you can even make it less than equal to h. No, then there will be a problem, sorry. Height exactly h. So for height h, what is the minimum number of nodes that your balanced binary tree can have? So what we will show is, what you were claiming is that this number should be 2 raised to h, right? You were saying that in height h, every level, the number of nodes doubles. So you like 2 raised to h or 2 raised to h minus 1. That is not correct. The correct function nh we have to find. If it was correct, then what you would have got is that nh is greater than or equal to 2 raised to h. So if the number of nodes is n, then n is greater than or equal to 2 raised to h. So h is less than or equal to log n. Right, that was your claim proof, which is not a proof. So we'll now make it now we'll correct it. So base case is n of 1 is what? For height 1, how many nodes are required? Well, 1 is also not bad. 1, yeah, you can do with 1. No, but the problem is we need height exactly h, exactly 1 height. So then you have to use 2. So n1 is exactly 2 in the base case. So it's the base case. So note that it can be, more nodes can be accommodated, right? You can go up to 3 nodes, but we are interested in the minimum. So 3 is also possible in height 1. So this is in height 1, this is the maximum that you can get. But n1 is not 3, n1 is 2. Because 2 is also fine. It's balanced. Okay. So we take the smaller option and now we do the recurrence. So for height h plus 2, so what is the picture for h plus 2? So you look at the root and you look at the subtrees. So left, right, and this part is unknown. This will go to the recursion or induction. Okay, and this is we are looking at only the root. So what are the heights? You want height to be exactly h plus 2. Okay, so let us say that without loss of generality, the right part of the root achieves height h plus 2. So which means that this height is how much? This is h plus 1. Now what can you say about this height? This can be h plus 1. Can it be h plus 2? It cannot be more than h plus 1. It can be h plus 1 or it can be less. Can it be h minus 1? Difference will be more, right? So that is what balancing tells you, that this is h or h plus 1. That's the BBT condition. Okay, so this is where we will get the correct recurrence. So the recurrence is then n of h plus 2 is at least, so 1 which is for the root, and then you have 2 subtrees. One of them is surely h plus 1 and the other one can be h or h plus 1, so it's surely nh. Okay, so this is the recurrence you get, that n of h plus 2 is at least 1 plus nh plus nh plus 1. Is that clear? So what does this remind you of?
So 1 plus nh plus 1 plus nh,
Which part would you understand? The 3 terms. One is for the root. this is for the height h plus 1 subtree, and third is the rest. So rest can be more than nh. It can be nh plus 1. So what you think as the first proof idea is nh plus, the rest is also nh plus 1, so you think of twice nh plus 1. But it may not be twice nh plus 1. If it was twice, then you will get 2 raised to h. But that's not the case, because in balanced binary tree we have some leeway, some error is there. But anyways, this recurrence is correct. This, or yes.
These NF can be only at the base level. No? If we do it before the base level, then it will not be.
There is no base level. We are talking about the root and its children. This is the induction step. We are not assuming anything about how these two triangles, the subtrees are. This part is hidden. But we have this guarantee from, well, just when you assume that the left subtree has at least height h, then essentially from the definition of nh function, you have this recurrence, right? This is not using anything other than the definition. What next? Exactly. So this reminds you of your first day here, which is, this means that nh plus 2 is at least the fib of h plus 2. So the sum of hth number in the sequence and h plus 1th number in the sequence, if you add it, then you will get the h plus 2th number in the Fibonacci sequence. Yeah, so it's strictly greater than. That's fine. So this is true. So the function n grows like fib, which we know grows. How does it grow? We showed that it grows exponentially. So it's actually even greater than, strictly greater than, and this is at least, let's say 1.5 to the h minus 1. H plus 1 here. Okay, so it's not 2 raised to h, but it is 1.5 to the h. That's the lower bound. So this is what we have shown, that nh is strictly greater than 1.5 to the h minus 1 for height h. Okay, this is how the tree size grows with height, and so which means that equivalently you know that h is then less than log of nh. Okay, so which means that for tree size n, the number of nodes n, height is at most log n. Okay, is that clear? So this is what we get. I mean, it was 1.5, I have made it log to base 2, it's fine because of the big O. So asymptotically it is still logarithmic in n base 2. But it's not exactly that, it's slightly more. There is a constant multiple. Yeah, so this is a very important thing, that if you have a balanced binary tree storage of your data, then the height is very, very small. Okay, this is a major departure from array, because so the term we used was q. It was q because the height there was n. But in a balanced binary tree, the height is now only log n. So it's an incredible advantage. So this is the right generalization of binary search. Okay. Any questions?
So, but commenting on the width of the research,
Mm-hmm.
it's like a trade-off, right? Like, so how does that storage work?
The trade-off, there is no trade-off. The actual storage is of size n.
No, but in an array, it's a size n, but it's going to be, or let's say it's a size n, but it's 1 cross n, right? But here it's going to be some width cross the.
But how will that matter? Or the hardest space you are using is always n. Nobody is claiming that we can store data of size n in hard disk smaller than n. It would be crazy. In fact, we will attempt that when we are ending this course. By that time, you will be so smart that you will be able to store big data in small hard disk. That we will try, but that is always with information loss. If you want perfect information, then you have to use ultimately n space. So this is, the space is still n. So there is no, that trade-off is not possible. I mean, in the sense that the space reduction is not possible. What you can reduce is some other search parameters. Like in binary search, you are able to reduce the number of rounds. That has now become height. Okay, height is the new binary search parameter. So this is a genuine progeny of binary search tree. Okay, is that clear? So this is the use of balance. And just one word about how you will implement this, let's say in C program. Binary tree. Well, for now we will cut the issue of balancing. That is a harder thing. We'll do it after a few weeks.
Sir, we are reducing the height because we want to quickly come from base to from.
Exactly. Yeah, that example we'll see very soon. But what I will not show you these 2 weeks is how do you actually get a balanced binary tree. Because as you insert numbers, getting this balance is a hard problem. We'll solve this after a few weeks. But the math is here, which supports fast search. So how do you implement this binary tree? You implement this by, as we have already mentioned, keeping pointers. 2 pointers, 1 value. And the whole tree is just the root. So keeping a pointer to the root. So this is what we call T. And each node is basically a struct. Keeps a value and pointer to left and pointer to right child. Okay, so schematically it is just, this is the struct. And this is P dot value. Okay, so P is any node P is basically, there is a struct pointer pointing to that memory space, and that memory space has 3 variables. You need minimum 3. This val itself can be a struct, because val may itself be data of a student, for example. So it will have name, roll number, tons of things. So val may not be an integer, it may be again a big record, but in abstraction it is again some struct. In fact, for current purposes, we'll think of p dot val as an integer. And the other two, p dot left, p dot right, are just pointers. Again, struct, pointers to struct. So in C programming, it will be struct star. Okay, so you have P is a struct, and then this struct inside has 3 struct stars. Is that clear? So this is the same as a doubly linked list. So inside a C program, it looks the same, but then when you step back and look at the abstract structure, it's completely different. Okay, so you should have that wisdom to step back and see what this abstraction is. Okay, in this level, there is no difference between array, doubly linked list, and tree node. Right, the atomic things are the same in C implementation, for example. So this is like so if it is looking exactly like doubly linked list or an array, where will the advantage come from? In building the directory. And then searching in it. Its original problem was that you may want to maintain a directory, which means it has to be incrementally built, inserted, updated, and when you want to search a name, it should be as fast as binary search. Right? So everything should be in log n. This was the goal. So why is that possible? Right? This we have not seen yet. So
we're reducing the search area by half every time.
But that is, yeah, so the key thing there will be, then you have to maintain a balanced binary tree. So we have to now see one more concept. So so balance is something we have already introduced. One more concept is needed. And then using balance and this next concept, so this next thing is called binary search tree. So search is the new word here. Previously we were talking about binary tree, balanced binary tree, and now balanced binary search tree. Okay, so 2 new concepts are needed on top of tree. So 3 new concepts are needed. With that, we will be able to build the directory that we wanted. But let us do this in small steps. So what is this search? What is BST? Have you seen this before? What is BST? What is the main property of BST?
The left element will always be smaller than the right.
Yeah, so there is a key value or there is a key in the record of each node, and you want the left child to be less than the parent, less than the right child in terms of that key. So was this done in ESC 101 or online? Binary search tree. Ah, yeah. Yeah, the way we invented trees, sure. Yeah, so but that we now want to impose on any tree structure. Any tree we will, any binary tree we will call a search by BST if this happens. So a binary tree T will be called BST. If for all nodes in the tree, two things happen. So every value in the left subtree, v dot left, subtree of v dot left, every value that you see there in there is less than equal to v dot val. And every value in the subtree of v dot right has to be right greater than v dot val. Okay, so left is less than equal to parent is less than equal to right. Okay, this is what makes a tree BST. Yeah, it can be done, but I think it creates some problems in some applications because the keys may not be distinct sometimes. So this part has to be less than equal to, this part has to be greater than. Okay, so when you have this happening for every node, then we call it a BST. Question? I mean, there can be applications where you want to use BST or non-distinct also. See, if all the values are distinct, then anyways the equal to cannot happen. So it's a vacuous thing there. So you can just think of less than and greater than. Okay, so what are the examples? So example of a BST is these are the key values I am writing down, not the full node. So 46 is the key value, left is 28, right is 67, and then it may grow on further. Then you will see some more complications that the definition has. Okay, so this is a BST because you start with the root, so 46, and you look at the left subtree. So you see the values 5, 28, 29, 35. They are all behind 46. Okay, and symmetrically you can look at the right part. But that is not enough to check. Okay, you have to look at other nodes also. So you also have to see what is happening under 28. Because for example, if under 28 on the left side there was 29, then that will violate, it will forbid the whole tree to be called a binary, to be called a BST. So you have to check each and every node, and you can check here that it's correct. So that is BST and a non-BST is similar thing. So what is the problem in this? Why is it non-BST?
29 is greater than 28.
Yes, so at the root 46, it is the check will happen, check will pass. 46 is fine. 35 also is fine because 35 on the left you have something smaller, and 5 is vacuously true. 29 is also fine. It's only this 28, when you look at the node 28, you will see the problem. That its left is fine, but its right has 29. Right? So to see the violation, you have to check each and every node. Sorry? It is actually a problem, yeah. So that I think I messed it up. It should be 27. 27, yeah. So the 4 ticks are fine. The cross explanation is that 28's right subtree has 27. Okay, so what the definition wants is that right should only be numbers more than 28. So 29 was fine, but 27 is not.
So then, in the green example,
Yeah.
46, the right subtree of 46 is 67,
40, yeah, okay.
and the left parent, the left child of 67 is 49.
67, yeah, okay.
So it even that counts, is it? Like, so when we are, I mean, I didn't understand the definition first.
The definition is you have to go at every node and look at the whole subtree on the left. Every element there has to be smaller than this node V. So when you look at 46, or when you look at 28, what should have happened is 28 should be less than 35 and 27, and 28 should be more than or greater than equal to 5. But this is wrong. Okay, the definition asks you to check this. You are at node, so V equal to 28. You should look at the left set and the right set, and they should be in order, which in this case is false. 28 is less than 27, that's false. Is that fine? Okay, so yeah, this is tricky thing. It's not just that you are looking at the 2 children, but you have to look at all the descendants. Okay, if any one of the descendants is a bad apple, then it's not a BST. Okay. Yes, so what is the use of BST? This is the definition and example, but why did we do this? So this concept is useful to search. Okay, because this is again abstracting out something from your binary search. So what exactly is it abstracting out? Yeah, so it is still carrying the idea of which direction to move. So when you are searching for X in this data structure, which is completely different from a sorted array, still there is this idea that if I want to search for X, then I look at 46, compare it with X, and if X is less than 46, I should move to the left direction, left child or left descendants. This doesn't mean that the number of left descendants is exactly half. Right? It can be a very skewed tree. So this is an abstraction only of one aspect, not of all aspects, which is why we need 2, 3 concepts. But this is giving you the direction in which to move. And then you come, let's say X is less than 46, so you will come to the left descendants, the left subtree. Next you will compare with 28. Right? So either x is equal to 28. So then you will say match. Or x will be less than 28, greater than 28, then you will move to either 5 or 35. So that's why this is a beautiful abstraction of search in binary search. So search for 29. So how does that work? So search for 29 will move in what direction when you start with 46? Yes, left. So you go to 28, from 46 you go to 28, then from 28 you go to 35, then from 35 you go to 29, right? So this is the pseudocode for searching 29 in binary search style. So although there is no sorted array, but just by the BST property, this random data structure also looks like behaves as an array, as a sorted array. Okay, it guides you which direction to go. Okay, and well, the property it satisfies is of course that if 29 is present in the data in this BST, it will be found. If the pseudocode doesn't find it, yeah, then it's impossible. So then 29 is not there in the BST, right? So that's the guarantee that it gives you. So it's found if and only if 29 is present. So it's a unique or deterministic way. So at no point do you have a choice. Okay, so when 29 is given, x equal to 29 is given, the algorithm is already hard coded. It will not be making any choices. Since it's not making a choice, so either it will find 29, or if it doesn't find 29, it will say that there is no 29. That is the guarantee you want. Okay, so let's write this pseudocode then. So T is a struct pointer, struct star type. X is, let's say, int. And you are trying to search X in the BST. So there is a promise that T is BST and X is int. Okay, so with that promise, the code is, pseudocode is initialize P to T and flag found is false to begin with. X is not yet found. So let's search for X. So while not found and P not equal to null pointer, so you are at the value P dot val. And so now this value you have to compare with X, right? So if this value is X, then what happens? Then set the flag. you have found X where you are currently present. Otherwise, you have to see where to move next. So P dot val is suppose less than X. Then what should you do? Yeah, so X is bigger. So you have to move to the right descendants, which means P has to be set to P dot right. Otherwise, okay, and so when this while loop ends, you should return what? Pointer P. Yeah, right. Or if, yes, okay, if found remains false, but you come out of the while loop, so it means that P was equal to null, right? So you will return the null pointer, which means that no location of X exists. Okay, so P is the location of X. This is the guarantee that you have. Okay, this ends the search pseudocode. Is this clear? So, yeah, what is the time complexity of this? So search T comma X will find X, and in time, yeah, so time that it will take is, it is only moving down from the root to potentially a leaf, maximum a leaf, right? It cannot go beyond the leaf. And it never moves towards siblings. It only moves from parent to child. So which means that it can never be more than height by the definition of height. So height of T. In fact, one can be more precise. It will be depth of P, which is at most height of T. So wherever X lives, if it lives already at the root, then it will take only one step, right? So depending on where X lives, that depth is what the time complexity is, which obviously is bounded by the height. And if X does not appear in the tree, then then in that case it has to go all the way to the leaf to get stuck. So that will again be maximum height. Yeah, and in the pseudocode it's P. P is the pointer, P is now the struct star where X lives. I mean, yeah, okay, P or location of X basically, Px. Think of that node where X lives. Any questions? Okay, so I think our time is anyways up. The harder thing is how to build this BST in a balanced way actually. That we won't be able to discuss for a few weeks. So, but let's anyways try to insert a node somewhere. So insert Tx, maintaining BST structure. How do you do that? Okay, search we have seen. If we can also insert new values, then we have a way to build at least the BST one by one as input is arriving. So suppose you want to insert 50 in that tree. How will you do it? Exactly. Yeah, that is good. So you have to do the search first. So you search for 50. So you will go from 46 to 67 to 49, and then you will come to 66. Yeah. So what you should do is since now you know that 50 is not there, right? So 50 is a new record. So you insert it on the left of 66. So let me not write this again. Let me just make this figure more complicated. So 50 will come here. Okay, so insert can be done just like search. So this is again same time complexity, same guarantees, and you have BST. Is that fine? So just let us just so do search.
We are not focusing on complete balanced.
Unfortunately, we cannot. The time for this is not ripe. So do search and then insert. Okay, so this is this also takes time. Yeah, depth of x bounded by height. Okay, so height is very important. This is why we very early on talked about balancing and making the height log, because all these operations now you see are coming as a function of height. So you can search and you can insert. So the next question is, what can height be, and when it is very bad, how do you reduce it? How do you keep it balanced, right? So this we'll discuss a bit next time, but we'll finish the pseudocode only after a few weeks.